please.
Thanks, Marco. Yeah, so thanks everyone for sticking around to the end of what's been a long but very interesting day of talks. Um, yeah, so I'm going to give an overview of the things that I've worked on at Topos for the past couple of years, as well as some of my current projects. And so since the aim is to foster collaboration between Chapman and Topos, I'm not going to go really in depth on any particular topic, but try to give an overview of some things. Hopefully, though, with an overarching theme. So my talk is about domain-specific logics for scientific modeling. I'll say more about how I think about that. Um, I want to start with this quote. This is a beautiful passage from the introduction to Nancy Cartwright's famous book on sort of disunity in science. And she writes, "We live in a dappled world, a world rich in different things with different natures, behaving in different ways. The laws that describe this work are a patchwork, not a pyramid. They do not take after the simple, elegant, and abstract structure of a system of axioms and theorems. Rather, they are apportioned into disciplines apparently arbitrarily grown up, governing different sets of properties at different levels of abstraction." And to a large degree, this is sort of the viewpoint that I'm going to take on science, that science is not a unified thing that where everything reduces to physics. I mean, it might in some sense reduce to physics, but the way it's practiced, the way we understand it, is not reductionist. Um, what but this talk is supposed to be about um, trying to introduce more formalization into science, and that might be seen as in tension with what I was just saying. And you can see it even in this passage, this contrast between abstract structure and so forth, with the rather than being apportioned into different things and so forth. So there's this common viewpoint that the usage of logic is inherently reductive. So you might think that if one takes as a premise that the practice of theorizing and modeling in the science is pluralistic, and I believe that's true, but then if the use of logic is inherently reductive, then it really has no legitimate role to play in the practice of science. It will inherently introduce a false kind of reductionism. And so what I want to suggest is that second point is actually not true. I could see how someone would have that conception, but I think from a modern point of view, particularly the point of view suggested by category theory and categorical logic, logic is itself best seen in a pluralistic way, and that there's not a single logic, but many of them. So to restate this vision in a more positive way, I think that there's a lot of room for the legibility and accountability and inclusivity and other aspects of science to be improved by making it more clear through the use of techniques from logic. And that to respect the plurality of science, this needs to be done using suitable domain-specific logics. So logics that are actually intelligible to people working on particular domains, that are phrased using the concepts and language that they find intuitive and natural in their subject. And that in order for this, though, not to be totally disjoint and ad hoc, we want to have some forms of meta logic to organize at least some of these domain-specific logics. And then as a hope, we could obtain perhaps passages or maybe even weaker notions of comparisons between logic. So there's perhaps some sense of unity, but nevertheless a lot of diversity. So to repeat a slogan that several of my colleagues from Topos have been saying recently, so we are aiming to do formal, interoperable, conceptual modeling, where for me, the conceptual is picking up on the idea that these logics should be grounded in the concepts of particular science, but they shouldn't just be totally disjoint from each other. There should be notions of interoperability both between and within logics, and that's where category theory can help us. So that's sort of an overview of sort of the sort of philosophy, if you will, that has informed a lot of my work. When I was here in Chapman in January for the philosophy conference, I talked more about how I think some of these ideas fit into classic problems in the philosophy of science. That's not what I'm going to do today. I'm not actually a philosopher. I'm an applied mathematician and I'm a software engineer. And so today I'm going to talk about my actual work on this stuff and what it looks like in more concrete terms. So, right, so my work at Topos has been broadly motivated by this sort of thing, and it tends to mix mathematics, particularly mathematics involving category theory and adjacent fields like logic and type theory, with software development. And I'm calling these theory and practice, but I put it in scare quotes because I don't really like that distinction all that much. To me, these are intertwined activities that should be mutually informing each other. So to give an outline of what I'm going to talk about, I'm going to first talk about some of the more established things that we've been working on for a couple of years and have made some, I think, interesting progress on. I'm then going to turn to a more recent project that I've been working on over the past year or so. And finally, at the end, I want to talk about some stuff that I'm just starting that I'm really excited about. Okay, so one of the things that we've been at for a while now is trying to realize some aspects of this categorical domain-specific logics idea within the Julia language. Why Julia? Because a lot of our intended applications have been in science and engineering, and Julia is a good language for scientific computing. We have built this framework called CatLab, which is a programming framework for applied category theory concepts, and we have used it to build a whole number of additional packages on top of it that target specific sort of languages and logics in different domains of science, and these comprise something that we call algebraic Julia. So we've done a whole bunch of stuff over the past few years. I'm just going to highlight a few of the things that I think have, a few of the things that I particularly like. So, one thing that we've spent quite a lot of time on, developed very extensively, and use as a basic tool in a number of our projects is this idea of categorical data structures, an idea with a long prehistory, but it certainly also involves my colleague David Spivak, who early in his career worked a lot on databases from a category theoretic point of view. So what we have implemented and extended those ideas in the form of a generic kind of data structure, which we use for all sorts of purposes. So I want to start by showing a little bit about how that works. So the basic outline of this thing is that you specify a schema, which is like some kind of simple theory, and that's done declaratively. So down here I have a very small, simple little schema. It's the schema for weighted graphs. So these are directed graphs with weights on the edges. And then, and in the top right, I'm showing a snippet of code of how you would write down that schema in CatLab. And what the system can do is take that schema and generate an optimized data structure for it, which you can think of as like a little database, but it lives in memory. And so here at the bottom is a tiny instance of data on this schema. So this is a weighted graph with 3 edges and 4 vertices. If you look at it, you can see that it's a simple kind of graph. It's a path graph, and there are some weights on the edges. And so the utility of this, so this is a very kind of simple example, but the utility of this is actually a quite flexible way of describing data structures. And if you know about category theory, you'll know that categories of presheaves or co-presheaves are extremely well behaved. They're some of the nicest categories out there. And they're also quite amenable to computation. And so we can compute lots of stuff in them. We can compute limits and co-limits and things like that. And these category theoretic abstractions are the basis for high-level computational tasks, like composing systems by gluing them together via co-limits, or doing rule-based rewriting and so forth. So to say this a little more precisely, if you ignore this business about data attributes, which adds a little complication to the formalism, the basic formalism for a database without attributes is extremely simple. A schema is just a small category. Usually, in practice, you would present it by generators and relations. And an instance of that is a functor into set. And then a morphism of instances is a natural transformation. And from the point of view of this talk, This is like the simplest of all categorical logics. It's the logic of a bare category. Usually one doesn't think about that as a logic, but you can. And it turns out that despite it being very simple from a traditional logical point of view, it's great for making data structures, and it's very amenable to computation. And so some of the things that can be expressed in this language include all manner of graphs and higher dimensional analogs of those, like simplicial sets or cubical sets. You can do a variety of diagrammatic languages that are commonly used in different parts of the sciences. So getting closer to something that actually maybe starts to look like something like what you might do in science. People use Petri nets or reaction networks often in biochemistry, in system dynamics, as well as in some parts of epidemiology, where we've worked a fair amount. People use stock and flow diagrams. Wiring diagrams are more of an applied category theory abstraction, but they can also be constructed using this kind of stuff. Right, so I got a little ahead of myself. So right, I was giving some examples of how these different flavors of categorical data structures appear in some different domains. This is a pretty selective list focusing on some areas that we've actually worked in with various collaborators. One example that I hadn't mentioned yet, because it's of a kind of different flavor, is that we've done some work in physics simulation, where we use these just as data structures to describe geometrical spaces. So that's a different usage. They're not specifying like a model like you would use a Petri net to specify a set of chemical reactions, but here they're playing the role of just defining the geometry to do a simulation. So right, and so part of the utility of having this kind of common abstraction that we can instantiate in different places is that we can reuse the same kind of patterns again and again in different places with pretty minimal effort. So like one of the things that we can do is, since we can compute colimits in these categories, we can make precise ways of specifying a model in a modular way, where you start with small pieces that are well understood and build them up using colimits. And dually, it's sort of less obvious what one does with limits maybe, but they can be used to do a thing called stratification, where you take, say, a model of an infectious disease, like an SIR type model, and say, well, actually, I want to now distinguish between people in different demographic groups, people of different ages or different genders, and you can use limits to factor your models in this way. And so this kind of gets back to a point that Xiaowei made about correct by construction, right? The point of this sort of thing is not that you couldn't do this without category theory. You can just grind through it. But the point of doing it this way is that it's correct by construction. You understand the individual pieces, you understand how they're composed, and therefore you can have some confidence that the large system that you build up is actually doing what you think you did, which you might not have if you just tried to do it all by hand in one giant spaghetti mess of model. Okay, so we like categorical databases. We've done a lot with that, but that's certainly not everything. So it's good for compartmental type models, like you find in biochemistry and epidemiology. It's not really so clear how you would use that sort of stuff to do the sort of like classic ODE or PDE based physics simulation. And so we've done some work on this where we use a different kind of diagrammatic language, which I won't get into too much, to formulate physics equations using the exterior calculus, and we sort of compile them into a simulator that applies the discrete exterior calculus to discrete exterior calculus operators on our geometric spaces, which are represented combinatorially as simplicial sets. And then finally, we have a piece that generates a computation graph and generates Julia code, finally generates Julia code to perform a simulation. So here I'm showing the results of of one of these. So it has a bit of a different flavor, but it's still emphasizing a similar philosophy of correct by construction, right? You want to specify the system at a high level of abstraction, that or rather at the level of abstraction that scientists in the domain want to think about it, and rely as much as you can on techniques of compilation or synthesis or however you want to think about that to produce a simulator that will do the computation. Okay. So as I was saying, the typical equations of physics that you might want to write down, everything from like Maxwell's equations to the Navier-Stokes equations, all that good stuff, you can't express in a synthetic or diagrammatic style in a category without further structure. So once you start getting into this, you're pushed away from the sort of bare categories that we were discussing in the context of databases to more elaborate kinds of categorical structure. So like a natural place to try to formulate just a perfectly general nonlinear equation might be a Cartesian monodal category, or if you prefer a sort of a slightly more syntactic view on that, maybe in a Cartesian multi-category. The sort of multilinear equations that you often see in mathematical physics are naturally formulated in a symmetric monodal category or a symmetric multi-category that you would usually want to also be have some additive structure as well. And so the point is not to drill down into any of these in great detail here, but to indicate that if we want to take seriously this idea that different kinds of scientific equations or scientific models are naturally expressed in a different sort of logical system, we want to ideally have a more systematic way of thinking about these things. So from the point of view of categorical logic, a particular kind of category with extra structure is a logic, and so we want a systematic way to think about those. The name that some people have used for this idea is a doctrine, which is sort of an unpleasant word, but I didn't make it up. What one's supposed to think is that doctrines are kind of categorification of a theory. So if we think that a theory or specifies a set or maybe some number of sets with some additional structure, a doctrine is like that, but one dimension higher. So it specifies a category or maybe a bunch of categories that together bear some extra structure. And so in the second part of this talk, I'm going to talk about some of my recent work over the past year or so to explore formalism for doctrines. And so a good chunk of this is joint work with my collaborator, Michael Lambert. This approach to doctrines we're calling double theories. And so doctrine, like the word doctrine, like the word theory, is not a single precise concept. There's lots of different ways to try to cash that out in something that's mathematically precise. And so this one is based on double categories, so that's why they're called double theories. And it has the interesting feature, among other things, that a double theory, so in order to be a doctrine, your category of models should actually be at least a two category, because that's kind of what it means in a way to be a categorical structure. You should form the objects of a two category. But this actually gives more than that. It gives you a double category of models. And so we think that the models of a double theory are themselves theories within that doctrine, and that the arrows between those models, those are a kind of structure preserving functor. Those are interpretations of one theory in another, or they could be interpretations of the theory in something that looks more like a semantics. So this is a familiar sort of idea from categorical logic. The pro arrows are some kind of structure preserving functor, and I really enjoyed this point in Drew's talk earlier, thinking that it's actually in categorical logic one frequently talks about interpretations, but it's a very strong thing to be able to interpret sort of one language within another. And so it's interesting to think whether these profunctors, which come from the theory, um, profunctors are often thought of as a kind of categorified relation. And so one thing that'd be quite interesting to explore more, which I haven't done, is whether you can actually use this, give these a nice logical interpretation. But anyways, so getting back to the main thread, one of the things that you can do with this notion of doctrine is systematize a number of the kinds of categorical structures that appear in what I like to call like the monoidal hierarchy. So these aren't traditional categorical logics. These are actually tend to be simpler than those. These are like simpler than a regular category, coherent category, or so forth. They're lower in the hierarchy, but they're very useful. And so these are some of the things that appear in there. So you have categories at sort of the bottom, which is where we started with when talking about categorical databases. There are all sorts of other interesting things in here. So a very classical and important thing, which is where categorical logic began, are Cartesian categories, which can be viewed as which correspond on the syntactical side to algebraic theories. And I mentioned earlier symmetric monoidal categories and symmetric multi-categories and stuff like that as a natural place to formulate certain kinds of other kinds of equations. So people have worked on doctrines in the past. So I want to spend a little time just situating this. So the standard notion of doctrine that has appeared in the literature is something called a two-monad. So it's a categorification of a monad on CAT. And this theory has been extensively developed by the Australian school. So people like Kelly and Lack and their collaborators and students. And so it's very powerful, but it's quite intangible in a way. And in particular, there's no simple way to present a two-monad. Like you can't like write one down just as like by generators and relations. And so the way I got into this was looking for a more tangible way to be able to write down a doctrine. And so double theories have this character that you can present them by generators and relations, not unlike the way you would present an ordinary theory in categorical logic by generators and relations. And so rather than being based on monads, they're based on functorial semantics, just like Leverrier theories are, but categorified. So this is two-dimensional functorial semantics. So just to say this in another way, you might know from categorical logic that there's correspondence between certain kinds of monads on set and certain kinds of algebraic theories. And so those are two different ways of looking at classical algebraic theories. So this thing that I'm working on is fitting into the bottom right square of this table. It's explaining how to categorify the viewpoint that you have in a finite product theory or a Leverrier theory. Okay, so I want to spend a little time just giving a hint of where this comes from. I'm not going to go into like lots of detail about it, but I want to give a little bit of a sense of like where did these ideas come from. So back in the 60s, I think Benabou observed that if you look at a lax functor from the terminal category, or I guess the terminal bicategory which is the same thing, to the bicategory of spans. So this is the bicategory whose objects are sets, and morphisms are spans, and two cells are maps of spans that fix the feet of the spans. That data of a lax functor is the same thing as a small category. And so as I understand the history, Benabou was the first person to introduce bicategories and lax functors. And this sort of example was actually one of the motivating things that made him want to look at this concept in the first place. And so it's interesting, and it also generalizes in a number of ways. And so it's kind of appealing to think that maybe, okay, so this is some kind of, this notion of a lax functor is giving us categories. So maybe could this be the beginnings of an approach to functorial semantics for doctrines? And not quite in this form. And the reason is that if you look at the sort of maps between these lax functors, the ones that are actually well behaved are these funny things called icons. And it turns out that those, if the lax functors correspond to categories, these icons correspond to identity on objects functors, which is a pretty restrictive and unusual kind of map to look at between categories. So in this form, this story can't really get off the ground. I think that's the reason why it was basically just kind of a curious observation for a long time. But what's interesting is that if you give yourself you give yourself an extra degree of freedom, and we say, okay, I'm going to look at a lax functor from the terminal double category to the double category of spans, which is a lot like the bicategory, except now in a double category you have two directions of maps, and one of them of one cells, and one of the directions is spans like before, but the other is now functions. And so that is again just a small category, because it turns out that the functions don't play any role when the domain of your theory is simple. But something really important happens, which is that now the right notion of natural transformation is between lax double functors. Because you have these functions available, you can actually get that these are functors. And so this, to me, is sort of the beginning of the story. It's saying that, well, I can think of the terminal double category as being a kind of trivial theory, and it gives me the doctrine of categories, just like the trivial theory in one-dimensional categorical logic gives you a set, which is like the basic building block, right? And so you can think, oh, well, now what I need to do is I need to say, well, first of all, I should generalize the domain, which is playing the role of my theory, from just the terminal to some other kinds of double category, like maybe one that's presented by finite, but by generators and relations. And then also I should be generalizing, just like in, you want to give yourself products or some other additional structures so that you can have more expressive theories. And so that's basically the sort of stuff that we did. And I just want to say one more thing about, just to give a little bit more intuition about why this is a natural approach to be taking. So it turns out that, so I was previously explaining how lax functors contain within them the concept of a category. What's quite cool is that a lax double functor actually already contains within it all four of the really essential concepts of the category, the four most basic concepts. So a lax double functor valued in span sends each object to a category. That's kind of a version of what I've been saying. It sends every arrow to a functor between those categories. It sends the pro arrows to pro functors, and it sends cells of the form on the left here, where you have identity pro arrows, to natural transformations. And more generally, if you have an arbitrary cell, it sends it to a map between pro functors, which is again a kind of natural transformation. So it really has all of these concepts sort of in there already, and that's what makes it a natural way to deal with doctrines. And so I think that's most of what I'm going to say about that. The big picture here, then, with that sort of motivation, is that a double theory is going to be some kind of small double category with extra structure. A model of a double theory is a structure preserving lax functor from that into span by default. But you can look at other semantics. And then it turns out, as I was saying before, that models of a double theory are the objects of a double category. Actually, if I'm being careful, I should say that it might be a virtual double category, and you can upgrade it to to even be an equipment or a virtual equipment if you've heard of those things. So what we've done so far is we've developed this outline basically in detail for several kinds of double theories. The ones that we call simple, which are just based on double categories without extra structure, as well as two flavors based on double categories with products. And what's interesting about this is that generalizing products from categories to double categories is perhaps has some twists and turns that one might not immediately expect. And there are actually at least two fairly plausible notions product, one of which is more flexible or general than the other. Okay, so yes, yeah, 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 yes, yeah, yeah. Yeah, that's a great question. I think very little is understood about this. I mean, so right, so in the classic setup, right, it sort of the the syntactic view came first, right? There were algebraic varieties, algebraic theories. Boissier recognized that those can be seen as categories with finite products, and that's the story. Then people identified other cases, like you had the typed lambda calculus, which had previously existed, and those are like Cartesian closed categories. And right, so in a lot of those cases, like the syntactic stuff was already out there, but that's not really the case because and I think there's some really interesting stuff to be thinking about here because you know the of what are the right sort of syntactical systems in which to understand this, because here we're starting with the categorical algebra first, which is yeah, 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 yeah. Thanks, that's a great question. Thanks. Okay, so I'm almost done, um, which is good. I think we'll leave plenty of time for questions, and it's also been a long day. So I'm gonna in this last section I'm gonna talk about what I'm just now starting to work on. Um, so and the goal is to take some lessons from all the work that we did in CATLab and Algebraic Julia, as well as to start to try to actually use this technology of double theories to do something. And the goal is to make a so one thing about CATLab is that it's really aimed at programmers. It's a programming framework, so you have to know how to program to use it, and you also need to know a bit about the underlying category. The more it turned out than I initially hoped one would have to know, and so you know so the aim of this new project would be to try to actually ultimately, it's my belief that these kinds of domain-specific logic should become accessible to working scientists and engineers and eventually other people, um, and they shouldn't have to know category theory. The system should be able to um, um, present the logic in such a way that whatever machinery is sitting behind it is totally is not visible. And so, I'm starting to work on some kind of interactive tool, which is supposed to support collaborative modeling and domain-specific logics. And I'm starting with some of the scientific and engineering domains that we worked in the past, because at least we have some experience with those. And the system is intended to take the form of a structure editor. So, um, so a somewhat textual interface, but which has a lot of scaffolding. And this is where I think some of the ideas that Xiaowei was telling us would sort of plug in. That right, like AI might play a role here in terms of providing suggestions or guidance or tactics. But to me, science is a human activity. It's about two things. It's about first it's about human understanding of the world and the universe that we live in, which is an intrinsic good, and it's about the transformative potential to increase our health and create more of the the basic material goods that we need to live comfortable and fulfilling lives. And so science, that's what it's about for me. And so modeling is a means to achieve those things. And so the tool is for people, and maybe AI will have some role to play in it. But I like to really think about languages and how and trying to design good domain-specific logics that feel natural to the people who work in those areas. And then from a technical point of view, I'm currently thinking that I will try to parameterize these domain-specific logics by double theories, but I want to get back to the original point of the talk. I don't want to suggest that I think that every language can be parameterized in such a way, because that's just sort of repeating at at the next dimension up the sort of reductionism that I suggested should be avoided. So I'm not claiming that any logic that you like could be written down this way. But what I do know is that a number of ones that I have worked in or wanted to have worked in can be described in this way. So I think it is a good starting point for a tool that involves domain-specific logics, but also provides some ability to interoperate between them. So to continue to motivate this sort of move that I'm making. So at the beginning of the talk, I showed how different kinds of combinatorial structures, these categorical data structures, could be used to represent different diagrammatic languages, or at least I told you that they could be used to encode things like Petri nets and stock flow diagrams and so forth. And that's connected to this insofar as it turns out that many of these diagrammatic languages, they can be thought of as combinatorial objects mathematically, but they're actually free categorical structures. So to give the example of this, which you will know if you're a category theorist, right, is that graphs in the category theorist sense are free categories. Another version of this, which has been worked out, there's several different flavors of this statement that have been worked out over the years, but Petri nets correspond to symmetric monodal categories of different flavors. And what I want to suggest is that these sort of things aren't coincidences. They arise because when you're drawing these sort of diagrams to represent a model or something, right? Those arrows typically represent transformations or movements of some kind. And so of course it's natural to think that those can be composed to express, you know, longer chains of interaction or transformation or so forth. So and of course composition is the thing that happens in a category. So it's sort of natural to make this move, and I think we can gain a fair amount by doing it. So in the first instance, even if we only care about the free objects, like we only care about Petri nets, we can still get a more flexible notion of morphism between them, which allows you to send, say, like a single transition in your Petri net to a whole composite or like string diagram of transitions in another one. And this sort of thing can be used to represent motifs, which are like commonly recurring patterns. That's a word the biologists like to use. They can also capture a notion of refinement. So Shalley mentioned refinement in his talk. And then it also sets us up to move to more expressive kinds of logical systems, the sort of diagrammatic equations that we were using that I alluded to earlier in our work on multiphysics simulations, as well as upgrades of the database story to involve things like sketches, or what my colleague David calls OLOGs, a kind of more expressive knowledge representation kind of thing, as well as a variety of other interesting languages that I won't get into. So that's the end of my talk. Thanks for your attention. Happy to take any questions. Yeah.
We have at least 15-minute discussion, so.
Thanks for your talk, Evan. Really enjoyed it. I may have missed something, but I was wondering if you could say a little more about schemas, their importance and desirable properties.
Sure. So schemas. So like, yeah. So here's a simple schema. So one way to think about it, the way we tend to use schemas is as a way to quickly spin up like domain-specific modeling frameworks, like especially in areas that compartmental type models, there's, you know, very often people are using a kind of diagram to specify the structure of the model, which they might then interpret, say, in ordinary differential equations or in some kind of stochastic semantics. And so this is a really useful common abstraction that you can use to say encode those kinds of diagrams as instances of a particular schema. And then because the system is parametric over the schema, certain operations that you might want to do on those models can be generic over all schemas. And so this is kind of just an example of using the power of category theory to achieve a higher degree of generality than one would typically achieve in this sort of situation. Like typically in software, one would make a library for Petri nets. And we do have a library for Petri nets, but it is basically just a fairly thin layer on top of this sort of stuff. Does that help?
It sounds
Yeah.
dangerously unifying, though, given your
Yeah, right. So
plurality.
there's this really funny thing. Yeah, I mean, like, I'm never quite sure how to frame it, because we want to be able to see commonalities between things, and we want to be able to, from a practical engineering perspective, right? Every engineer, every software engineer, they're always looking to try to avoid duplicating code, repeating themselves, sharing functionality. So, right, it's useful to have common abstractions that you can reuse, but somehow it doesn't follow from that all these things are actually the same, and it doesn't even follow that the people using the Petri nets need to know that they're part of some other general thing, and it also doesn't follow from that everything that you could want to do, you could be doing with, say, these categorical data structures, which I was arguing later in the talk you can't do either. So there is this interesting back and forth of, like, you want to try to find commonalities and common abstractions, but that doesn't imply that everything is the same thing. Yeah.
Question?
I'm interested in these double theories, and it's a cluster of questions basically about how to understand what I might term the relationship between, like, algebra and algebraic notions and topological notions.
Mm-hmm.
So one way of approaching this might be, like, is there a double theory for the category of post sets, or the double category of post sets, and, you know, order preserving maps and weakening relations? Another way might be, let's see, let me just look at what I noted, actually. Probably the most efficient way to ask the question. What might finite limit theories? Like, it's interesting.
Yeah.
Want to do some notion of categorical doctrine, and in the sort of one-dimensional setting, you have to move to finite limits to get a notion of category. Yeah. But here you're doing it internally. You're internal to the categories, so you get categories for free.
Yeah.
But what would happen if you
those are both
limits, and then
those are both good questions. So I'll start with the second one. So, right. So I said that double theories can do, like, so the sort of Cartesian or finite product double theories that we've been doing can do the sort of doctrines on this slide. They don't actually yet cover a lot of the richer doctrines that people would often think of in categorical logic, and in particular, they don't yet cover finite limit theories precisely. And it's what you're maybe sort of imagining, that you need to have you need to put more limits into your double theories, presumably, in order to be able to express the limits that you want to have in its models. And there's a lot of work to do to sort of figure out how all that works. And in fact, in some sense, the theory of limits in double categories has been around for a while, but people are still finding out lots of new things about it. So this actually gets back to a point that I was trying to make before. It's that like, it's not just like there's not one kind of theory, right? There's not just one kind of double theory, right? There's a whole hierarchy of those two. And it's turtles all the way down. That's how that stuff works. So as to your first question about relations, so I think I actually should have accidentally glossed over this. So when I was talking about this idea about lax functors sending objects to categories and these other notions from category theory, this story, part of the utility of the functorial semantics viewpoint, in this case, double functorial semantics viewpoint, is that you can replace span with other double categories. And in particular, you can get internal or enriched categories by replacing span with suitable other things. So in particular, you can take matrices over the Booleans as your target, as your semantics, and then it makes everything, instead of being categories, they become posets. And so all this stuff, or not, sorry, they become preorders, is what I should say. And then all this stuff becomes, instead of being for categories and functors and so on, it becomes like, preorders and monotone maps and these weakening relations. Those are what correspond to profunctors. So some of that stuff is contained in here, although it certainly doesn't tell you the sort of connection that we were talking about with regular categories and ordered. Like you're not going to get that for free, but like you can at least get a lot of the basic structures you can get sort of by turning the crank on this sort of thing. Yeah. Yeah. Yes. Yeah. But there are often multiple ways to do things. So like for the enriched theory, you can transfer it to your semantics. That's one way to do it, is try to put it in the semantics by using matrices over some monodal category V, which is your base of enrichment. But another thing you can do is put it into your theory. So if you're one of the most common kinds of, so that helps you for certain kind, there's a certain common set of examples of enriched categories, which are basically, the Hom sets are sets, but with extra structure, extra algebraic structure. So maybe they're enriched in like abelian groups or commutative monoids or whatever. So for those sorts of examples, with this notion of finite product double theory, you can also put that into the theory. So there's not always a single way to set things up, and there's some flexibility about what goes in the semantics versus what goes in the theory, which is a general feature of categorical logic. And yeah.
Hi, hello. Thank you so much.
Yeah.
It was really a very interesting talk. How can I learn those functionalities that you implemented in Julia?
Well, this is a very timely question because some of my colleagues at Topos in particular, someone named Priya has just finished writing a book about the work we've been doing in algebraic Julia, which I think is not quite yet publicly advertised, but I think will be soon. So I'm really excited about that, hoping that will be a good entry point. In addition to that, if you go to this website here, algebraicjulia.org, I don't think it advertises the book just yet, but it does have some blog posts and papers and other resources if you want to look at that. Yeah.
Evan,
Mhm.
just to show that we are not a completely closed community and we have differences. Can you put back the hierarchy of the symmetric and the monoidal? Because, you did mention that one. You did mention that this is not traditional
It's not true.
categorical.
Yeah.
And, there's lots missing, right?
Yeah.
There's polymorphism, there is modal logic, there's calculus of constructions, the lambda, all this
like
stuff is not there.
no.
But the question I have is about the Markov category, because that is also debatable. Because
Yeah, so this is a little bit of a fudge. Like okay, so I okay. So if I want to be really careful at what I'm saying, Markov categories in the standard form that they appear in the literature, like in Tobias Fritz's work, are not a model of a double theory. You need to rejigger things slightly. And the reason for this is that Markov categories do something which is really, from a category theory perspective, feels kind of odd, which is that they stipulate a family of operations, the diagonal or copying operations, that are not natural. And one of the things that I was touting as a virtue of this is that this machinery makes by construction makes everything be functorial or natural or so forth by construction. And usually that's what you want, but in that case, it's not. And so you actually, what you need to do to make that example work is change your viewpoint a bit and say that a Markov category is not something that you get by subtracting from a Cartesian category. I should actually put this arrow in the other direction, but a Markov category is, you start with a Cartesian category, that's your base of deterministic morphisms, and on top of it, you put your non-deterministic ones. And if you arrange things this way, then you don't need to do weird stuff like put non-natural operations into your theory. So thank you for, you're on the ball. Good job. So you honed in on that.
It's just to show that, we are friends, we love
Yeah.
each
Yeah.
other's work, but there are differences.
Yeah.
Please.
Yes. And right. So as I also noted in response to Brendan's question, that like to get to these higher level and also more traditional categorical logics, we have to go further. Yeah. 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 Yeah.
So thank you very much, Ivan.
Yeah.